For number 2, it tells us that this is circle P, so that means P is the center. We're finding the value of x and assuming segments that appear to be tangent are tangent. So FE is a tangent. It only touches circle P at one point, and that's point E. This particular problem you can work 2 different ways, so I'll show you both ways and you can look at which one you care to use. So the first one is using the radius tangent theorem, which says that when you draw a radius to a point of tangency, it creates a perpendicular relationship. So you know you have a right angle here, which means you can use the Pythagorean theorem on this right triangle. Now, you know one of the legs is x, one of the legs is 12, and for the hypotenuse, from P to G is another radius. So it is also has a length of x, just like PE does. And so now we can set up our Pythagorean theorem by leg squared, x squared, plus other leg squared, 12 squared, equals the hypotenuse squared. So the hypotenuse is that entire length from P to F, which would be x plus 8, not 8x. You add the parts to get the whole length, and you have to square the hypotenuse. So leg squared plus leg squared equals hypotenuse squared. So on the left side, you have x squared plus 144 for the 12 squared. Remember, when you square a binomial, you're multiplying that binomial times itself. And so you're not just squaring each one of the terms. So when you distribute, you get 4 terms when you multiply a binomial times another binomial. So the x times the x is x squared, x times 8 is 8x, 8 times x is another 8x, and 8 times 8 is 64. You don't have to worry about factoring a quadratic since you have an x squared on both sides. It will simply cancel out by subtracting x squared from both sides. So we have 144 on the left. The combining of like terms of 8x and 8x gives you 16x plus 64. So when you subtract 64 from both sides, you get 80 equals 16x. Dividing by 16 gives you x equals 5. So that's one way to find the value of x. Now I'll show you a different way of finding the same value of x. Here we have a tangent segment intersecting part of a secant segment. I can make this a secant by just extending this side all the way to the other side of the circle. So now this whole length of the segment would be a secant. I can also label this part from P to this point on the circle as x, since it's also a radius. So now I can use the relationship of whole times external of the secant equaling whole times external of the tangent. And we know that when we do whole times external of a tangent, it really means you're just multiplying the tangent by itself. So that's the tangent squared, is another way of saying that. So the whole length of the secant is not the x plus 8. It's from this point to this point. So it actually is the x plus 8. X plus x is 2x. So it's 2x plus 8 is the whole length. So the whole length of the secant would be the 2x plus 8. And then I'm going to multiply that by the external part, which is the 8. So I'm going to put this in parentheses to remember to distribute the 8. On the right side, the whole times external of the tangent is the 12 times itself, or 12 squared. So when I distribute the 8, 8 times 2x is 16x, plus 8 times 8 is 64, equals the 12 times 12, which is 144. So if you'll see, we have the same exact equation here that we did over here now. So again, subtracting 64 from both sides, we get 16x equals 80, and dividing both sides by 16 gives us x equals 5. So you can use the radius tangent relationship to make a right triangle and use Pythagorean theorem, or you can use the fact that all radii of the same circle are congruent to create another radius of x here, and use the secant and whole times external relationship here. Whole times external, whole times external. Both get the same answer.